Okay, so any questions from the last time? Maybe I should mention that, so today I will finish this chapter, okay. Then we should have a midterm exam based on just these two chapters, first two chapters, right. I mean, what is your preference? I mean, it's up to you. Huh? I think that to have two exams is better, because, you know, maybe for some reason you don't perform well in one exam, then you can, you know, recover in the second exam, right. And besides also, I mean, this is a long course, right. So in the midterm exam, we'll just ask questions on these first two chapters, and the final exam, it will be the last two chapters. Huh? So that way you don't have to, I mean, if there's one exam including all these four chapters, it becomes too much, right. So what we will do is that, okay, I think there will be still the tutorials will continue for next week also on this chapter. So maybe you can, you know, maybe we can have the exam after 2 weeks. So you have some time to prepare this first two chapters. And no, but then I mean, then it will be what you could do. I mean, you want to do 3 weeks, because you see, in between I'll also start teaching the third chapter and so on, right. So it will be a bit of a problem for you, because I mean, you will start concentrating on the third chapter, and then you may start forgetting, you know, some of the things from the first two chapters. So that's why I think it is better not to delay it too long. No? But I mean, if it's up to you. If most of you feel 3 weeks, okay, fine. So a majority agree? Okay. First two chapters. These two up to complex analysis, up to today. Yeah. Yeah. So okay. So 3 weeks. So then I will fix a time with the, I mean, the date with Patricia. I mean, so maybe I think November 1st is Tuesday, so November 8th, maybe November 8th. Huh? Okay. Okay. Any questions from the? So last time we did the saddle point approximation, right? And we in particular looked at one example, and that example will be useful today. Okay. So today what we'll discuss is the gamma functions. So this is the gamma function. Okay. And it's there are several ways of defining it, this thing, but I'll just follow this this exposition in this notes. So the definition is the following: the gamma z is defined by this equation, is 1 over 2 pi I, and a contour integral of the expression e to the t divided by t to the z dt, right? So what I'm integrating is t. Z is fixed. Z is some complex number, okay, and we are integrating t. So t is also a complex number, and I'm integrating in the t complex plane, right? Complex plane t, and the path, the contour that one is choosing. Notice that this is a branch cut, right? I mean, in general, z is not necessarily integer, right? Z is any complex number. So obviously there is a branch point at t equal to 0, right? And at t equal to also infinity, right? So you can choose a cut as you wish, but it is convenient to choose a cut along the negative real axis. So I choose a cut like this, okay, all the way from 0 up to minus infinity. So this is a cut, huh? Branch cut. Okay, and the path that is chosen is the following: you go below the branch cut from all the way from minus infinity to here, then go around this branch point, and then go like that, okay, all the way up to minus infinity again. So the lower part of the branch cut, go around and then come back from the upper part of the branch cut. So this is the definition of the path. And now I have to also specify which sheet we are talking about. So we'll choose the sheet where the t, so if I write t as a modulus of t times e to the I theta, okay, then in this sheet that we are discussing, theta goes from minus pi by 2 to plus pi by 2, minus pi to plus pi, okay. So the theta goes from minus pi to plus pi, okay. So this lower boundary of this cut has an angle minus pi, and the upper one is plus pi. Okay. So we choose this particular sheet.
If we choose minus pi, theta should be greater than or equal to minus pi, then I think we should say less than pi, right?
Less than.
Less than pi.
Yeah. Okay. I mean, there is a line here, right? I sort of I basically cut it, right? So yeah. It's I mean, yeah. Okay. So this is the definition. Okay. I mean, so this is a definition of gamma z. So it's a definition. Now, some things you can try to, I mean, you can immediately deduce. For example, if let's say, so let's try to find some properties of this. First thing that you see, I mean, I can start doing some kind of a partial integration. So the way to do this is that you can write 1 over t to the z as d by dt of 1 over t to the z minus 1, right? But then I have to divide by z minus 1, right? So 1 over t to the z as 1 over, so minus z minus 1, right? Times this, I mean, times this. Because when I take d by dt of this object, right? I mean, this is nothing else but t to the power of minus z minus 1, right? So when I take a derivative of this, I will get here, this will give me minus z minus 1 times t to the power of minus z minus 1 plus 1. Minus 1. So that this minus 1 and minus 1 cancels, and we just get t to the minus z, right? So this gives you t to the minus z, which is that, and this factor cancels that factor. Okay. So I can write it like this as let's write, so this integral e to the t. So instead of t to the z, I write it as minus z minus 1. Okay, and d by dt of 1 over t to the z minus 1. Okay, dt. So along this contour, 1 over 2 pi I. So this is my gamma 1 over gamma z. Okay. Now you do a partial integration. Okay. So there will be a boundary term, but boundary term will vanish. I mean, so this whole thing I write. Okay, this I can take it out, right? Because I'm integrating t. Z is just a constant number as far as the integral is concerned. So you get here minus 1 over z minus 1 times 1 over 2 pi I. And one term will be d by dt of this whole thing, which is e to the t times t to the z minus 1 dt. That's total derivative, minus, again, integral, but not d by dt hitting that e to the t, right? So that will give me just e to the t divided by t to the z minus 1 dt. Right? I mean, is that clear? And I just took this out. In fact, let's look at this object. So this d by dt acting on that is, there are two terms, d by dt acting on this, which is that term, so that gets out, and the other term will be d by dt acting on this, which is this term, right? So that's indeed the expression. Now this one, so both are in the contour C. This one is obviously 0 because you see the end points are what? End points are minus infinity, right? Either minus infinity minus I epsilon or minus infinity plus I epsilon, right? But in both cases, e to the t will exponentially become 0, right? T goes to minus infinity, so this becomes 0, right? So this vanishes, and what is left over is that. But if you now look at this minus cancels, and 1 over 2 pi I e to the t divided by t to the z minus 1, this integral is by that definition, is simply 1 over gamma z minus 1, right? So we see that this whole thing is 1 over gamma z minus 1, but there is also this prefactor, which is z minus 1, right? 1 over z minus 1. So we get this relation that 1 over gamma z is equal to that. So I just take the, so this means that, so one relation is gamma z equal to z minus 1 gamma z minus 1. This is an important relation. I mean, this is just simple, just a partial integration, nothing more. Just do a partial integration. Okay. The second property is okay. We said there is a branch cut, right? I mean, there's a branch cut for arbitrary values of z, right? But what if z is an integer? If z is an integer, there is no branch cut, right? So we can try to evaluate this 1 over gamma, but gamma evaluated for z equal to n, right? That's much easier to calculate. So there is no branch cut. So if z is an integer, let's say n, which is an integer, then there is no branch cut. That means this integral will cancel that integral, right? I mean, this part of the integral. So what will be left over is simply this little circle integral, the small circle integral around the origin. So therefore, this contour essentially becomes, because these two parts, I mean, this contour initially had three terms. One was the, let me just call it the lower boundary of that, the upper boundary of this, and then this little circle, let's say of some radius epsilon. Let's call it gamma epsilon. Okay, these are three parts of the contour. So this contour is the lower part plus the upper part plus the integral over the small circle. Right? Now, when there is no branch cut, these two will exactly cancel, right? Because they are in the opposite orientation, they will cancel. So these two will cancel for this case, and what you are left with is just this. So, but this integral is just going to pick up the pole, the residue at z equal to 0, right? So now if you look at this, I mean, if this n was a negative integer, suppose n is a negative integer, there is no singularity here at z equal to 0, right? So the first conclusion is that if n is less than, in fact, less than or equal to 0, right? Because also for n equal to 0, there is no residue, right? So in that case, this integral is 0, which means 1 over gamma n in such case is 0 for n less than or equal to 0, integer. I mean, I'm only talking about integer now. However, if n is positive, suppose n is greater than 0, strictly greater than 0, in that case there is a singularity here, right? Nth order pole, okay? And then you can compute the residue easily. All you have to do is because remember the residue is just the coefficient of the first order pole. When you make a Laurent expansion, this coefficient d minus 1 is the residue, right? So all you need to do is just expand e to the power of t, right? So expansion of e to the t, I mean, this is near t equal to 0. So this is simply t to the power of k over factorial k, summed over k, going from 0 to infinity, right? Where by definition, the factorial 0 is just 1, okay? I mean, that is the convention we are using, okay? So then so if z is some positive n, then in order the residue is simply given by the coefficient of 1 over t, but that will appear when you choose the term when k is equal to n minus 1, right? Because when the t to the n minus 1 from here will cancel from the t to the n part of it, and finally what will be left over is 1 over t, right? So therefore, in this case, this integral, so 1 over gamma z, gamma n, simply becomes, for n positive, it simply becomes the coefficient of k equal to n minus 1 term, which means 1 over factorial n minus 1, right? 1 over factorial n minus 1. Okay. So this is the other important property. Gamma of n is factorial n minus 1 when n is a positive integer, is a strictly positive integer. Is that clear? This is so. I mean, let's write down explicitly a bit. So the integral that we are doing. So the object that we are integrating over here is there's a 1 over t to the n, which is from here, and then e to the t So let's write it down, 1 plus t square by factorial 2 plus t cube by factorial 3, and keep going. There will be one term which will be t to the n minus 1 over factorial n minus 1. Then the next one will be t to the n over factorial n, and so on, right? Now, from this, remember, I mean, so let's multiply this out, and we want to, the residue is simply the coefficient of 1 over t, right? Now, if you multiply this with that, there is no pole at all, because that's in fact a regular term, right? So actually the 1 over t will come from when you multiply this with that, right? But then the coefficient is 1 over factorial n minus 1. Right? And in fact, there is a 1 over 2 pi I also, so that's exactly, I mean, otherwise the integral would have been 2 pi I times the residue, but that 2 pi is cancels. I mean, that's the reason why we put 1 over 2 pi I here. Okay, so this is the thing. And from here, you also deduce one thing. I mean, if 1 over gamma n for n less than or equal to 0 is 0, that means the gamma n is infinite, right? So the gamma, so gammas have this property that at all the negative, I mean, gamma of 0 is infinity, gamma of minus 1 is infinity, gamma of minus 2 is infinity. All of them, all of these are infinity. Okay. Right. Notice that this relation is consistent with that, right? I mean, you can immediately check that these two are consistent because, after all, I mean, if you substitute that there, suppose z is equal to n here, then what that relation is saying is that gamma n is equal to n minus 1 times gamma n minus 1, right? But this, well, from this thing, we see that gamma n is factorial n minus 1, and here it is n minus 1, and gamma of n minus 1 will be factorial n minus 2, right? But this is an identity, right? I mean, this times n minus 1 is factorial n minus 1 by definition. So these two are, of course, compatible. I mean, as it should be. Okay. Now, what else I have to say here? Yeah. Okay. So this is one integral representation for the gamma function. Okay. But it turns out that for many physics problems, the integral representation which appears more frequently, more often, is a different one. Okay. So let me define that. Of course, the two are equivalent, which we will prove. But there's another representation for gamma, which is given in terms of this integral 0 to infinity e to the minus t times t to the power of z minus 1 dt. But this integral makes sense. I mean, it's well defined only for the real z, real part of the z. I mean, real part of the z greater than 0. Okay. This is easy to see. Why? Because, okay, so let's say at infinity there is no problem because this is exponentially suppressed. But the problem is at 0, this becomes 1. I mean, at t equal to 0, this becomes 1. And then you have here t to the z minus 1 dt, right? So if the real part of the z, I mean, imagine, for example, z was real. If z was less than 0, this would be singular, right? dt divided by t to the power of minus 1, and then, I mean, something more negative than minus 1, right? That would be singular. I mean, dt divided by t to the power of anything 1 plus epsilon. This is singular at t goes to 0, right? For any positive epsilon. So that's why the real z should be greater than 0. Right? Also, for epsilon equal to 0, it's also divergent. It's a logarithmic divergence. So we really need real part of z positive, strictly positive. So this is this integral is whereas this integral is defined for any value of z. You see, there's no problem with this any value of z here. Okay. Because anyway, you are not actually going through the point origin, right? This is a contour encircling the origin, so there is no problem with that integral. So it is defined, well defined everywhere. And at minus infinity, this is exponentially suppressed. So this integral is well defined for any value of z. Yeah, and for any value of z, this is a finite expression. I mean, there is no, it doesn't blow up anywhere. What it means is that the fact that this never blows up, it means that gamma z is never 0, right? So it has no 0 anywhere in the complex plane, but it has infinities. Whenever n is negative integer, it has infinities. Okay. Fine. So this is, as I said, this expression appears many times, and let's again try to make sure that, for example, this relation is true. Okay. Of course, we cannot check this relation because our condition is already real z is greater than 0. Okay. So this we will not be able to see, but we will be able to see both of these things because they are in that these are, I can check in the domain where this is valid. So for example, let's look at the first relation. So this I can again, it's a matter of again doing a partial integration. So again, write this as a 1 over, let me see, maybe this time I should do the other way around. So let's write this as minus d by dt e to the minus t, right? This guy is the same as that. Okay. And then I still have t to the z minus 1 dt, integral 0 to infinity. Now this is the same as I do a partial integration. So there is one is a total derivative term. So there is a d by dt of the whole thing minus e to the minus t times t to the z minus 1 dt, and then I have to subtract the other piece when the d by dt hits there, right? So that means it minus makes it plus, so plus, and d by dt acting there gives you z minus 1 times t to the z minus 2 e to the minus t dt. Okay. So again, this is a partial integration. Just this is the boundary term, and that's d by dt hitting there gives you this. I mean, there is a minus sign when you do that, but there is already a minus sign here, so it makes it plus finally. Now this is this object is by definition gamma of z minus 1, right? So it's again z minus 1 times gamma z minus 1, which is the right hand side here. Okay, and this term is again 0 for the same reason. For the real z positive, this is 0 because at t equal to infinity there's exponential suppression, right? I mean, this is a boundary term, right? This is a total derivative, and at t equal to 0, this one vanishes for real z positive. Okay. So okay. So this is again, I mean, satisfying the same condition, and to check that is also clear because I mean, you just take. So let's see if you can. This is just doing just step by step. Keep doing it. So in other words, you start from gamma n. So you can keep doing recursively gamma n equal to n minus 1 times gamma n minus 1 using that relation. Okay. Then again use repeatedly this relation. So you keep getting n minus 1, n minus 2, gamma n minus 2. Keep going all the way, and finally you will get n minus 1 all the way up n minus 2 all the way up to 1 times gamma 1. Okay, but when you have gamma 1, this z equal to 1 here, so this 1 cancels. So you just say integral of e to the minus t dt, which is simply gives you 1, right? I mean in this limit. Okay, so gamma 1 is 1. Okay, so I mean gamma 1 is 1. Which you can explicitly integrate. And so this whole thing just gives you again factorial n minus 1. Okay, so this is also fine. Okay, I mean still we don't know whether these two agree. So what they are saying is that this integral and that integral gives you the same values for z for z positive integers, the same value. But that doesn't imply that this is same for arbitrary value of z. Also, it shows this very powerful relation, but still, we have not proven that the two things are equal at this stage. We'll need to do a few more steps here. One thing you can see also that, I mean, this, you see, z is just a complex number here, right? But it's actually, as a function of z, this is also analytic in z. Okay? The reason is you can take a derivative here. I mean, remember what what you have to check is gamma of z plus delta z minus gamma z divided by delta z exists. I mean, this is what we have to check, right? If it exists, the limit delta z goes to 0. So delta z goes to 0. It exists. It's unambiguous, meaning it does not depend on which direction you are coming, right? This is the. But so this you can work it out. Let's see what is gamma of z plus delta z. This is simply e to the minus t to the power of z minus 1 plus delta z, right? dt, integral 0 to infinity. So when you take the difference between these two, so that the numerator becomes, I mean, this numerator becomes, you have the integral 0 to infinity e to the minus t, I mean this minus that, right? So t to the z minus 1 is a common factor, and then you get t to the delta z minus 1, and then divided by delta z dt. Okay. I mean, I'm just taking this minus that. So t to the z minus 1 is a common factor, but then there's a t to the delta z left from here, and there it's of course 1, so it's minus 1. Okay. Okay. And now we can make an expansion. After all, t to the power of delta z, t to the delta z is the same as e to the power of delta z times log t, right? So I can make an expansion. This is 1 plus, I mean, delta z is small, delta z log t plus higher orders, plus order delta z square. Okay. So now substitute that there. This 1 cancels that 1. Okay. So this, it starts with delta z. Delta z cancels with delta z here. Okay. Higher order terms you don't care because there's a delta z squares and so on. So okay, one power will get removed here, but still there will be some delta z left over. And finally, I'm going to take limit delta z goes to 0. So that does not matter. And then the only issue then is whether the first term, when you, I mean, delta z cancels. So what is left over? The integral is e to the minus t to the z minus 1 times log t. So question is whether that integral is finite or not. Okay. And that integral will be finite again for this choice for this same reason. So question is the following. Okay, let me repeat that. Once you expand it, maybe I should erase something here maybe. So once you, so therefore then this right hand side of this equation, so limit delta z goes to 0, gamma of z plus delta z minus gamma z. This is simply the integral e to the minus t to the z minus 1 times log t, right? Because this is a log t term. I mean, delta z cancels, but there's a log t left over. So the question is whether this integral makes sense. I mean, is it finite or not? Well, that you can see that at infinity this is exponentially suppressed, so there is no problem. Again, remember this representation exists for real z positive. This is where this is defined. I mean, that representation exists. So anyway, for t infinity there is no problem. This is exponential suppression. Okay. At t equal to 0, again there is no problem because I mean this is of course 1, but since the real part of z is positive, right? I mean, do you agree? I mean, so this is the expression something like t to the power of I mean log t divided by t to the power of 1 minus some quantity, let's say epsilon. Let me just say, suppose real part of z is epsilon. Okay, epsilon is positive. Okay, so then this expression is that, and this one is finite. I mean, there's no problem with that, and so long as epsilon is strictly is not equal to 0. Okay, it's positive. Oh, I'm just so that we can see it more clearly. I mean, this is t to the power of epsilon minus 1, right? Yes. Take suppose z is real. So just z is equal to epsilon minus 1. I just rewrite it as 1 minus epsilon. Nothing. I mean, just to because yeah. I mean, it's the same expression, right? I am saying t to the power of epsilon minus 1 is 1 over t to the 1 minus epsilon, right? You can just leave it also as that, it does not matter. So, this expression is not divergent at as t goes to 0, right? Because it is true that log t goes to infinity, but that I mean, suppose log t was not there. I mean, what is this expression? The integral of that is simply t to the power of so what is t to the power of epsilon, right? Yeah, t to the power of epsilon divided by epsilon, right? If I just integrate that expression, this is what you get, right? But then, okay, there is also a log t sitting here, but it does not matter because so I mean log t becomes infinity, but I mean any power of t is always goes to 0 faster than log t goes to infinity. Okay, this I mean yeah, is that clear to you? I mean, the one way to check that, you agree that exponential function goes faster than any polynomial of t, right? So, you can just take the exponential of this. If you just take the exponential of that, you get e to the power of t to the power of epsilon and then log t, e to the log t, I mean times log t. No, I do not know, how shall I say this? I mean, what I am trying to say is that log of t is let's see, it's much less than t to the power of minus epsilon, right? That is what we are saying. Okay. So, I mean, as t goes to infinity, log t goes to infinity. This also goes to infinity, but this is much slower. This grows to infinity much slower than that. Okay. And that you can see by just taking the exponential of the both sides. So, you get here t is less than exponential of t to the minus epsilon. Okay. It's I mean, these two statements are the same. The statement that exponential function grows much faster than any polynomial, taking the log on both sides, you see that a polynomial, I mean a t goes much faster to infinity, 1 over t goes much faster to infinity than log t. So, this you can see. So, the upshot is that this is well defined. This integral is well defined. I mean, this finite integral, right? So, therefore, the differential exists. So, we are saying that d gamma by dz is defined, is well defined. Okay. Right? Of course, we are always assuming real z is positive in this entire thing. Right? For real z positive, this is well defined. So, this is analytic function. Okay. Now, okay, what else one can say? Now, of course, I mean, so this here we are saying is well defined for real z positive. Okay. But now one can ask the question, suppose I want to, can I analytically continue to all complex plane? Okay. So, this analytic continuation appears here now. So, let us see how we can do that, and this we can do by using this property here. So, let us see, I can I mean I can write this object as gamma of z plus 1 equal to z gamma z, correct? Now, I can keep repeating it. So, let me invert it. So, this means gamma of z is equal to gamma of z plus 1 divided by z. Yes, I mean just divide by z both sides, you get that expression. Now, I can keep repeating it again and again. So, just so I get 1 over z. Now, this again I use repeatedly the same equation. So, I will get gamma of z plus 2 divided by z plus 1, right? I mean just use the same equation, but now for z replaced by z plus 1, right? So, then you get gamma of z plus 1 is gamma of z plus 2 divided by z plus 1. So, I just replace now gamma z plus 1 by that, all right? And you keep going. So, you will find 1 over z plus 1, 1 over z plus 2, all the way up to say 1 over z plus n minus 1 times gamma of z plus n. Right? You keep repeating this again and again and again, the same relation. Okay. Now, if you look at this expression, I mean, this right hand side, this numerator, the right hand side, this is well defined. I mean, this is analytic for z, real part of z, let's see, greater than minus n, right? Because what we want is that that integral was well defined whenever the argument, the real part of the argument was positive, okay? But the real part of this argument is real part of z plus n. So this should be positive. That just means the real part of z is greater than minus n, okay? So the right hand side is analytic for in that range, right? And all this, the denominators are also analytic so long as z is not a negative integer, okay? When z is a negative integer like z equal to 0 or z equal to minus 1 or z equal to minus 2, there are poles, right? But stay away from the poles, okay? Then this is also analytic, okay? So that means and this defines to you what is the gamma z for real z greater than minus n, okay? So this is the idea here. So I mean, just pictorially, if you try to draw a picture of this, essentially what we are saying is that here is my the z. I mean, so this is the real part of z. So initially we defined the real part. I mean that integral made sense for real part positive, real part of z positive, right? So on this side it was making sense. But then I can use this relation or this relation to relate a point, a gamma at some point here to. I mean, you see this kind of relation gives you gamma of z in terms of gamma of z plus 1. If I know gamma of z plus 1, then I know gamma of z by using this relation, right? So, so the value here can be obtained by considering the value at z plus 1, right? So say this is my z, some point z. This is z plus 1, then the z plus 2, and so on, right? So this is determined if I know the gamma here, the value of the gamma function here. Here it is determined if I know the value of the gamma function there, and so on. So successively you keep adding integers until you arrive at some point which is the real part is positive, right? Now here I know what it is, because I mean I know in the sense that the integral is defined there, right? That will give me some value. If I could do the integral, it will give me some value, and then from there I can just go back and deduce the value there, you see, and that will be the analytic continuation. So you analytically continue that whole thing, the entire complex plane, right? Except for, of course, the negative integers, right? For negative integers, there are poles, which we anyway knew that even the first definition of the integral for gamma function had that property. That for negative integers, there was poles for the gamma functions, right? So this is what. So this way you can. So actually, also this argument says that in fact in the entire complex plane, gamma function is analytic, except at the 0, minus 1, minus 2, etc. The negative integers. There are poles, and in fact first order poles. You can see that from this relation, the first order poles. Okay. I mean z equal to 0. This is a first order pole, right? At z equal to minus 1, this is the first order pole, because other things are finite at z equal to minus 1, and so on. So at each negative integer, there is a first order pole. What else? Okay. So now there is a very again another useful relation for gamma function, which we will again obtain starting not from this definition of the integral, but from the other definition of the integral of the gamma function. So let's again write that expression e to the minus t to the z minus 1 dt 0 to infinity. Okay, this is the expression. Now, there is one relation which says that gamma of a, okay, times gamma of b. A and b are complex numbers. So this, so you just substitute z equal to a here for this one, and z equal to b for this one. Divided by gamma of a plus b is equal to something called a beta function. There is a definition. Okay, this is called the beta function. And have you seen it before? Probably not. I'm not sure. And this object is equal to t to the power of a minus 1 and 1 minus t to the power of b minus 1 dt from 0 to 1. Okay. So the claim is that this object, this ratio, is equal to that. Okay. That's the thing. Okay. So we want to prove that. I mean, there's a question mark here. Okay. We want to prove that this ratio is equal to that. Okay. This will be again very useful. So how do we prove this? So let's take the definition of gamma a, and so let's compute the numerator of this expression, right? So gamma a times gamma b. Well, this is nothing else 0 to infinity e to the minus say t. Let's say t1, because I have two integrals here, right? So I choose the dummy indices, t1 to the power of a minus 1 dt1 times 0 to infinity e to the minus t2 t2 to the power of b minus 1 dt2. Okay. Now let's change some variables. Let's call t1 equal to say x square. Okay. And t2 as y square. Okay. It's a change of variable. So then this expression becomes 0 to infinity. So you have e to the power of minus x square. Now that one is x to the power of x squared to the power of a minus 1. So x to the 2a minus 2. Okay. And finally dt1 becomes 2x dx, right? I mean, this implies dt1 is equal to 2x dx. So 2x, so there is a factor of 2, okay, and then 1 power of x, so that makes it 2a minus 1 dx. That is from here, and exactly the same expression, I mean, same thing will happen here. So there will be another factor of 2 coming from there, which will make it 4, and then you have e to the minus y square, y to the power of 2b minus 1 dy. 0 to infinity. Okay. Now you put them together and think of this as a and define the following. So let's say x equal to r cosine theta and y equal to r sine theta. Let's define that way. Okay. Then you get here this expression is equal to 4 e to the minus x square minus y square. So e to the minus of x square plus y square, which is simply e to the minus r square, right? So this gives you e to the minus r square. And okay, here you get r to the power of 2a minus 1 from here, but there is also r to the power of 2b minus 1. Okay. I should also mention dx dy. I mean, this is just a polar coordinate going from the Euclidean coordinate to the polar coordinates, right? So dx dy, I don't know if you remember, is simply r dr d theta. Right? This is the polar coordinates. So there is an extra factor of r coming from there when you change the coordinates. Right? So there is an extra power of, I mean, plus 1, okay, time dr. That is the r part. But there is then, of course, I have also to keep track of the thetas here. So you get here cosine theta to the power of 2a minus 1 and sine theta to the power of 2b minus 1 d theta. And what is the range? Well, see, thinking in terms of this, what is happening? X is going from 0 to infinity and y is going from 0 to infinity. So if you draw the picture, it's like this. So here is my x and y. So, this is going from 0 to infinity, that is also going from 0 to infinity. So, I am integrating over this quadrant. So, here the theta is going from 0 to pi by 2, okay, and r is going from 0 to infinity. So, this is going from 0 to infinity, and this one is going from 0 to pi by 2. Right. So, we have reduced that integral to this form. Okay. And the final step is again, you see this integral is almost like that integral, right, this type of integral, except that it is r square. So, let us again call r square is equal to t. Okay. Now, look at this integral, this part of the integral is very similar to that, the original integral which was in the gamma function, except that here it was e to the minus t, here it is e to the minus r square. So, let us again call r square as equal to some t. So, what can I erase now? Maybe here. So, let us call, so r square is t, which means r is equal to square root of t. I define that. So, this part of the integral becomes e to the minus t, and yeah. So, this gives you, I mean dr gives you 1/2 over root t dt, right, when you look at the derivative. So, you get here the dr gives you dt divided by 2 root t, and from here, okay, this 1 has cancelled with the minus 1. So, t to the power of a plus b, because r square to the power of a and r square to the b, right. So, that is t to the a plus b, but then there is a minus 1 here. Okay. So, that minus 1 gives you simply 1 over root t, right. So, root t makes it 1 power 1. So, that makes it a plus b minus 1, but that is exactly 1/2 of gamma of a plus b, right. So, the conclusion is that, so therefore, okay, so what we have found, what we conclude is that gamma of a times gamma of b, which is what we started with, after a series of change of variables and so on, we find there is a 4 divided by 2. So, it's a 2 is 2 times gamma of a plus b times this integral 0 to pi by 2 cosine to the 2a minus 1 cosine theta to the 2a minus 1 sine theta to the power of 2b minus 1 d theta. Okay. Yeah, this is that correct? This factor of 2. Must be right. So, now, so if I divide now both sides by gamma a plus b, so then we have the relation, this is equal to this quantity. Yeah, sir. Yeah, here you mean this line here? Yeah. So, I mean, yeah. So, minus 2 plus 1, which is minus 1. Yeah. Right. Okay. So now the last step was just to show that. So, this is what we said is beta function, right? But the expression that we wrote for beta function was t to the power of a minus 1 minus t to the power of b minus 1 dt and 0 to 1, right. But you can easily go from here to here, simply write t is equal to cos square theta. Okay. So, then let me see, yeah, t equal to cos square theta probably. So, let us see, so what will I get? So, I will get from here 0 to 1 cos to the power of 2a minus 2, right, I mean cos square to the power of a minus 1, cos theta to the power of 2a minus 2, and here you get 1 minus cos square theta inside, which means sine square theta, right, again sine square theta to the power of that. So, sine square theta sine to the power of 2b minus 2 And then finally dt, dt just gives you minus cos theta sin theta. So it's not the 0 to 1. I have to figure out what is the range of the integral. So this gives you when you take dt, dt is equal to minus cosine theta to minus 2 cosine theta sin theta d theta, right? So that also but when you substitute that here for dt, you see that 1 power of cos theta and sin theta appear, right? So 2a minus 2 becomes 2a minus 1, and 2b minus 2 becomes 2b minus 1. Okay, and then what is left over is minus 2 here and d theta, right? But what about the range? See, when t equal to 0, theta is pi by 2, right? And when t is 1, theta is 0. So the integral here is from pi by 2 to 0. But then you can change the thing and remove the minus sign here. So it makes it 0 to pi by 2. So that's exactly that expression, right? So I mean, this expression that I wrote before is the same as that. And this is what we wanted to prove, that this ratio is equal to that. Or equivalently that. These two are the same expressions, just change of variable. This is a very useful equation, because we will obtain a very important equation starting from here. Is there any question here now before I erase this part? It's just a series of change of variables, you know. Because I mean, what was the aim? You see, I mean, here you have two integrals of the gamma function type integrals, right? But the denominator had only one gamma function. So basically, from this whole thing, I wanted to factor out one integral which was exactly like the gamma function integral. And that is the reason why we went through all this, going to the polar coordinate. I mean, first of all, replace this by x square and that by y square, and then go to the polar coordinate. And then for the radial direction, the integral just becomes like the usual gamma function integral. So you can identify immediately that with the gamma of a plus b. And it's also clear that when you do that radial part, it will add up. This a and b will add up, right? Because both of them will come with the radius, no? Radial part. And then there is some angular integral left over, so that is what it is, this part. Okay, this is the. So it was just nothing deep, just some technical steps, I mean, for changing the variables and so on. Okay, but this has a very, I mean, from here you can deduce an amazing amount of information. So for example, let's choose from this equation a equal to, well, I don't know which is better. So a equal to say z, and b equal to 1 minus z. Suppose you choose this particular values. Okay. Then this one is gamma of z times gamma of 1 minus z divided by gamma of a plus b, which is gamma of 1. But gamma of 1, you know, is just 1, right? So this is simply 1. Okay. That is equal to, we are saying, the integral 0 to pi by 2 of so cos theta to the power of 2z minus 1, and sin theta to the power of 2 times 1 minus z minus 1, right? Because b is 1 minus z. So if you open this bracket, 2 times 1 minus 1, which is 1. So this thing is the same as 1 minus 2z d theta. So it's exactly the opposite power to that. Negative, I mean 2z minus 1, and then this is just the negative of that. So this whole thing simply becomes cotangent theta to the power of 2z minus 1 d theta. This is the integral. But this integral we have already worked out, actually. If you remember, I mean, you remember when we discussed the multi-valued functions, we gave one example of how you integrate, how you can use that to integrate. Right? In fact, it was this function we were integrating, except that we were not using these variables. I think we were using another variable. Also, we can again go there to that variable. So if I just call cotangent theta as some t. Now, I mean, t is appearing too many times. Okay, I don't know. U, let's say. Okay, then so what is d? So let's take the derivative of this. So I'm changing the variable. Cotangent theta is equal to u. So what is the derivative of cotangent theta? So it's a cos x square theta, right? Cos x square theta d theta equal to du, right? Is there a minus sign? I mean, I always get confused with. So basically, I want to differentiate cosine theta divided by sine theta. So if I take that, so first thing it acts here, so it gives you minus sine theta divided by sine theta, which is minus 1. Is that correct? Sine theta, yeah. And then the other term is plus cosine theta, and then take a derivative of this, so it becomes minus sine square theta, and then the derivative of sine theta, so cos square theta. This is what it is. No. Yeah, correct, right? So then this becomes, if I take out sine square theta as a common factor, so the sine square theta plus cos square theta, which is 1. So there's a minus sign, okay? There's a minus sign. So this is the change. But what is this object? I mean, you remember that cosec square theta is the same as 1 plus cot square theta, right? Cot square theta is cos square theta divided by sine square theta, and this is how we got this relation. This relation is that. So I can rewrite this. So therefore, it is the same as 1 plus u square, right? Because u is cotangent theta. Okay. So this relation, this tells me that d theta is d minus du divided by 1 plus u square. Okay. So this expression becomes, so there is a minus du divided by 1 plus u square that comes from the d theta. Okay. And this is simply u to the power of 2z minus 1. And now the range of integral, once again, there's a factor of 2, sorry. When theta is 0, cotangent is infinite, right? Because it's cosine divided by sine. So sine becomes 0. So this is infinite. And when theta is pi by 2, cotangent is 0. So you get 0 here. So once again, this minus goes out and you can exchange the limit. Okay. But this was exactly the integral we did for the in that. Yeah, correct. Yeah, that integral that we had done was something like the integral which we, I think in the, I don't know, the multi-valued functions. When we discuss multi-valued function, we had done the integral x to the p minus 1 divided by x square plus 1 dx from 0 to infinity, and that was pi by 2 sine. Cosec, 1 over sine, pi p by 2. Okay. So this is the expression. So we had exactly done that. So now you just have to just replace p by 2z. That's all. This was defined. This was what was the range? P was between 0 and 2. So between 0 and 2. By the way, that also you can see here. I mean, in these expressions we have used this integral representation, right? Which means both the real part of a and real part of b are positive, right? So this equation that we had obtained was really valid for real a and real b, both of them positive, right? But now I'm taking a equal to z and b equal to 1 minus z. That means real part of z must be positive from here, but also real part of b, which means real part of 1 minus z. So 1 minus real part of z should also be positive, right? which means which means that, I mean, you have taken the other side, so real z is between 0 and 1, that is what it means. So, I mean, twice the real z, I mean, real part of the 2z will be between 2 and 0, which is exactly that range there, because remember p is 2z, here is 2z and there was p. So, just replace p by 2z, okay. So, that is exactly the range where you can trust this equation, right, and also where this has been calculated. So, we can just substitute this now here, and just substituting that. So, you get this 2 cancels with that pi by 2. So, it becomes pi, and then 1 divided by sine pi z, right, because p is 2z. So, this is the expression. Okay. This is a very important, very, I mean, useful relation actually. So, let me just write this relation here. So, what we are seeing is that gamma z times gamma of 1 minus z is equal to pi divided by sine pi z. Actually, now you can see immediately what is the singularity structure, right. If you take, for example, z is, whenever z is an integer, this blows up, right hand side blows up, right. But whenever z is an integer, positive or negative, it does not matter. So, suppose it is positive integer, well, then this is finite, we know, right, but then this becomes infinite, right. Similarly, when z is negative integer, this one is finite, but that one blows up. So, this is for all integers, this is divergent, and that is indeed what you are seeing here. Furthermore, you can also deduce the singularity structure. For example, let us say if I look at z equal to 0, I want to see how this behaves. So, suppose z is very close to 0, z near 0. So, I want to study how these functions behave near z equal to 0. Well, near z equal to 0, gamma of z, so let me divide by gamma of 1 minus z. So, we are saying gamma of z is equal to, this is in general true, but now what I will do is I will expand this expression near z equal to 0. I mean, this is just rewriting that, just divide by this. But now I am going to expand it near z equal to 0. So, the leading term at z equal to 0, this is finite. It's gamma 1, which is 1, right. So, the first term is simply there is 1 here and then pi, and then sine pi z. When z is small, sine of theta, when theta is small, is theta, right. You just make a Taylor expansion for the sine. So, that gives you this pi over pi z, right, plus finite terms. This is the only singular term, the Laurent expansion. Finite terms. I mean, you see what I am saying. So, here gamma of 1 minus z is finite near z equal to 0, because gamma 1. So, I can expand gamma of 1 minus z equal to gamma of 1 plus 1 minus z, or z minus 1, z times derivative of gamma, d gamma over dz at z equal at 1, and so on. Okay. So, I mean, this is the denominator. So, when you make an expansion, when you make a Taylor expansion, this goes up in the numerator, this z's, right. Leading term is simply that. Okay. All the other corrections that you will find will be in finite terms, okay, because there you get positive powers of z, which will cancel with this z, so that you will get non-negative powers of z. When z equal to 0, yeah. But argument is 1, you see. So, maybe I should write, yeah, it's, yeah, it will be some coefficients. Let me just write some coefficients, a1 plus z square a2, etc. And then, in fact, you can actually calculate so this immediately tells you that the residue is simply 1, pi cancels, just 1 over z, right. So, residue at z equal to 0 is 1. you can, for example, now let's look at when z is say minus n, where n is some positive integer. Then you get again from this equation gamma of minus, so z is close to minus n. So I don't know, write z is equal to minus n plus epsilon. So then this becomes minus n plus epsilon is equal to pi divided by sine pi times minus n plus epsilon, okay, and then gamma of 1 minus z, but that is gamma of 1 plus n minus epsilon, right. This is finite, okay. I mean, this is a positive, and since n is positive, I am taking n to be positive integer, this is something finite. And here what happens, I can use again trigonometric relations. So sine of, so this is my sine of pi minus n plus epsilon is the same as minus sine pi n minus pi times epsilon, right. I mean, if sine is an odd function, I just use that fact, it's an odd function. And then this is equal to sine pi epsilon with pi minus. So it depends on, yeah, so there is a minus is here, then there is also a minus 1 to the power of, let's see, when n is odd, so let's say n is equal to 1, then there is a no sign. Sine pi minus theta is the same as sine of theta, but sine of 2 pi minus theta is minus sine theta, correct. So when n is odd, there is no further sign here, right, no sign comes, but when n is even, then there is a sign. So it's a minus 1 to the power of n plus 1. So this whole expression becomes this becomes pi divided by minus 1, so this is same as minus 1 to the n, okay, sine pi epsilon, and then gamma of 1 plus, I mean, the leading term is simply gamma of 1 plus n, for in epsilon goes to 0 limit, which is factorial n, right. So now if you expand sine pi epsilon near epsilon equal to 0, then you find the pi cancels, so you just get minus 1 to the power of n over epsilon times factorial n, okay. So the residue is that near z equal to minus n. At z equal to minus n, this is the residue, okay. So this way you can get, I mean, so this equation is quite useful to extract a lot of information about the singularity structure. If you try to draw gamma function, of course I cannot draw on a complex plane, but suppose that z was just real, suppose z is just real, so I am just looking at the real axis and try to, so x, so z is say just x, I put the imaginary part of z 0. So then if I try to plot gamma function, it behaves like, okay, at x equal to 1, gamma 1 is 1, right, gamma 1 is 1, gamma 2 is also 1, right, gamma 2 is also 1 because gamma 2 is 1 times gamma 1 from the one of the recursion relation that we had, right. Then gamma 3 will become 2 and so on. So here anyway, here it's all finite in this part, but then at 0 we know that it diverges, at that near z equal to 0 it went like 1 over z, right. So in particular for the real part it's just because 1 over x, so this will go to infinity as x goes to 0, right, the gamma function, and here it's all finite, but it grows, right, but for any finite value of x it will be finite, right, but as x increases it will exponentially grow, okay. We will discuss that, the growth, how it grows. We will, I mean, you remember that when we discussed Haddle point last time, I gave you one example, right, actually the Stirling formula, right, it will be Stirling formula actually, so it will be very fast growth, very rapid growth, there. But nevertheless it's finite everywhere for any finite value of x. So here it's this. Now go to minus 1, there you see, okay, now let's look at this here. We say near z equal to 0, gamma of z behaves like, is basically 1 over z plus regular terms near z equal to 0. So, near z equal to 0, right? That's so now we are saying, but what is z? Z is simply, I mean, z is 1 over x plus I y, right? Now, of course, I have set y equal to 0. I mean, because I'm looking at, to draw this plot, I have set y equal to 0, right? I'm just looking at how the gamma function depends on x. So I've set y equal to 0. If y equal to 0, so when x is positive, of course, when x is positive, it's in plus infinity. Right? But when x is negative and approaching 0 from negative direction, it's minus infinity, right? So the picture here is like this. I mean, it doesn't go to 0, somewhere like that, between 0 and minus 1. Okay. Then this, for the same reason, from between minus 1 and minus 2, it will be like this here, and so on. This is what, I mean, that's why there is this alternating signs here in the residue, minus 1 to the n. And we also know that gamma function never becomes 0. Remember the discussion we had? So it will never cross this axis. No? If it's, once it stays positive, it stays here positive, then negative or positive here. So this is the kind of kind of plot you would find for the gamma function. Okay, now so now let's finally go back to try to see that the two integrals that we have written for the gamma function, they are the same. Okay, we want to show that. Of course, yeah. I mean, so remember the first integral we had defined was on this contour. Where there was a branch cut here from 0, right? And this expression was e to the power of t over t to the z dt. That was expression, I think, 1 over 2 pi I. This was an integral definition where the contour was given by this. And remember this was, I mean, the argument of t. Argument of t is, you know, have I ever defined argument? Argument is simply this. I mean, if you write t as modulus of t times a phase, this is argument. Theta is argument here. Okay. So the theta was as we said, was going between minus pi and plus pi, right? As you go from here to here. This was for the lower boundary, and this was for the upper boundary, lower boundary and upper boundary. Okay. So now from here, we want to show that this gives you the same answer as the second integral, but of course second integral is defined for real z positive, right? So I can only show this correspondence for real z positive, because second, yeah.
This is 1 over gamma k.
Sorry, this is 1 over gamma z. Correct. Yeah, this is 1 over gamma z. Exactly. So the second integral was gamma of z was equal to e to the minus t to the power of z minus 1 dt from 0 to infinity. Right? This was the. So first of all, okay. So how I will, and this was defined for real z positive. This is defined for all z, but that is defined for real z positive. So what we want to show is that if I take this integral for real z positive, then I can rewrite that that integral becomes equal to that. This is what we want to show. Any question? Okay, so how we will do this? Let's rewrite this expression. Let's change the variable, because this is in that. I mean, here I have chosen a negative cut, right? So the integrals were from minus infinity to 0, whereas that integral is from 0 to infinity. So it's very easy to change. Let's see. We want, in fact, let me see what exactly the change was. E to the power of minus I pi. Yeah. So I write t equal to e to the minus I pi t prime, okay, times t prime. I mean, I have to keep, it's not enough to just say minus t prime, because there are, because of the branch cuts and so on. So you have to give the precise, the phase. Yeah, that's crucial. So now you can see, so once you do that, this expression becomes e to the minus t prime, because here I can just replace this by minus, because there is no fractional powers here, right? But down here I have to be careful. So this simply becomes e to the power of minus I pi z, from substitute that, and t prime to the z. And dt just gives you e to the minus I pi, so that's a minus sign here, times dt prime. And then there is integral 1 over 2 pi I, and there is integral. But let's see what is the integral. Now, so there's another. So this is the t plane. This is the t plane. This is the t plane. Let's draw the t prime plane. So here is my t prime plane. Okay. So for the lower guy, remember, for the lower boundary it was theta was pi, right? E to the I pi. So when I write e to the minus I pi, that is the same as let me see. No, the lower one is e to the minus in the lower boundary you have minus pi. So t was modulus of t times e to the minus I pi, right? So t prime, since t prime is e to the I pi times t prime is, for the t prime the angle is 0, argument is 0, right? So this lower boundary basically just goes here, 0, and the upper boundary is it was e to the I pi, but then there is another e to the I pi, so it gives e to the 2 I pi, right? So in the t prime, again of course there is a branch cut, but now the branch cut is from 0 to infinity, positive infinity, and the range argument of the t prime, here the argument is 0 on this boundary, and on this boundary argument of t prime is 0 here, and here argument of t prime is 2 pi. So that is the sheet that we get. Just starting from this sheet, which was defined here, I just make this coordinate transformation, and then I find in the t prime coordinates we are in this sheet, the t prime. Right? There's a branch cut. I mean, this branch cut goes over to that branch cut, because of course t is minus t prime, right? So all this negative real axis becomes the positive real axis there. So the cut is there, and the precise range of the argument also you see is going from 0 to 2 pi there. So the range, that is a sheet that we are discussing. And then we have this expression here. Okay. Now we use this fact. Okay, let me write it like this. In fact, maybe I should have started from 1 minus z, but it doesn't matter. So this is what we have is 1 over gamma z. So this is 1 over gamma z. Okay, and this is along this C prime contour. The C prime contour here. Okay, so let us now try to evaluate these contours. I mean, so what is the C prime contour? There is the this upper boundary, lower boundary, and the circle, right? So here you have like this, here, and this circle here, gamma epsilon. Okay. So this contour, this is the sum of 3 terms. So minus 1 over 2 pi I, integral over this small circle surrounding the origin, okay, of e to the minus t prime. E to the minus I pi z, I take it out because that's outside. So minus 1 over 2 pi I times e to the I pi z. This I just take it out of the integral, and then what is left over is e to the minus t prime over t prime to the z dt prime over I mean in this circle gamma epsilon plus let me see, I think we should start from that's the mistake. I mean, not mistake, but I mean, yeah, okay. So let me do the following. I will, yeah, I need to do two things actually here. So the strategy is the following. I will use this equation gamma of z times gamma of 1 minus z. This is equal to pi divided by sine pi z. I will use the relation. Okay. So and then just put this gamma 1 minus z down here. So what we are saying is that gamma of z is equal to pi divided by sine pi z 1 over gamma 1 minus z. Okay. This is a strategy now. Now I will use this integral representation for 1 over gamma 1 minus z. Okay. And then obtain the relation for gamma of z, which will turn out to be that equation, the second integral, I mean, right. So whatever I have done here, I mean, just take this for 1 minus z. So instead of evaluating, because I want to use this one represent this object in the first integral representation. Okay. So I just take it 1 minus z. So this z is replaced by 1 minus z here. So just do everything wherever you see z, just replace by 1 minus z. Okay. So this is gamma of 1 minus z. This is 1 minus z here, and this is 1 minus z. Correct. Yeah, that makes sense. Okay. So and then you have again from the lower boundary. So lower boundary is say yeah, just right, just lower boundary. So times e to the minus t prime to the 1 minus z dt prime, and finally the last one, upper boundary. Okay, this is the expression. So let's look at each of these terms, and now I'm going to set real. See, we are looking at real z positive. Okay, so again, once again, so real z is positive. That is where I will have, I mean, this integral defined. That's the only place, right? But this integral is defined for any value of z. Okay, so what I'm going to do is that in this expression, I will just take real z positive. Okay, so okay, this expression is perfectly fine for any value of z. So I just use that. Then you get this. But now I'm going to set real z positive. So what is this expression? This, in fact, this expression is simply exactly that. You see, what is this integrand? Integrand is e to the minus t prime. Just take it up, right? So t prime to the z minus 1, right? I mean, this is the denominator 1 minus z. So just take it up. So there's a minus, and then dt prime. And the statement is that this first integral vanishes in the limit the radius goes to 0. Okay. Which you can see because if you just take, so in this integral, I mean, t prime is simply epsilon times e to the I theta, right, on this circle. So there will be, this you can ignore because epsilon is small, so this is almost close to 1, so this is not important. Here you get a power of epsilon to the z minus 1, right. From the change in the measure, you get an epsilon. So altogether you get a power epsilon to the power of z minus 1 plus 1, which is epsilon to the power of z, right? And for real z positive, that vanishes. So this behaves like epsilon to the power of z, right? This by changing the thing. And for real z positive, this vanishes. Okay. So, this vanishes in that limit. And now we are just left with these two integrals. So, let us see, where shall I can erase this here. So, all of this is for 1 over gamma 1 minus z. So, we are saying is 1 over 1 gamma 1 minus z is equal to there is a minus e to the I pi 1 minus z over 2 pi I, and I have this integrals which is e to the minus t prime times t prime to the power of z minus 1 dt prime, but dt prime now. So, what is here you see in the lower boundary, t prime is simply the modulus of t prime times e to the 2 pi I, right. So, let us look at so here in the lower boundary, remember, so in the lower boundary t prime is the modulus of t prime times e to the 2 pi I, and for the upper boundary is t prime is equal to modulus t prime, just modulus of t prime, because angle is 0, argument is 0. So here I will get everything is modulus of t prime times e to the so what is this expression? So, in the lower boundary this is e to the power of minus t prime. T prime is now just a real, because I am going the real line here, you see the real line times e to the 2 pi I. So, that is that, but here it is t prime to the z minus 1 times e to the power of 2 pi I z minus 1, right, and then dt prime just gives you dt prime, because that is it. So, in the first term you have a factor e to the power of 2 pi I z minus 1, okay, and the integral is from 0 to infinity. Is that the direction? Yeah, 0 to infinity. Okay. In the second integral, I have no phase, because argument of t prime is 0 here. Okay. So, it will be simply the integral e to the minus t prime to the z minus 1 dt prime from, but now from infinity to 0. Okay. Infinity to 0. So, this was the lower contribution, I mean the boundary, the lower boundary contribution, that is from the upper boundary contribution. Okay. Is that clear to everyone, or is there some question? I mean, what I am doing, I am integrating this expression in the lower boundary and the upper boundary. In the lower boundary, t prime is the absolute value of t prime times e to the 2 pi I. Okay. So, I have to substitute that. When I substitute that, I get this extra e to the 2 pi I z minus 1 factor. Right. Okay. And then the integral is just all the t prime is now just real, just real. I mean, there is no extra phase, just real objects. Okay. In the upper boundary, the argument of t prime is 0, so there is no extra phase appearing there. That's all. And this limits are just coming from the arrow orientation. This is going from 0 to infinity, and that one is going from infinity to 0. Okay. This is that. Fine. So, now let us put everything together. And you find, so this is okay, minus e to the I pi 1 minus z divided by 2 pi I, and this is e to the power of 2 pi I z minus 1, and here just change orientation, there is a minus sign 0 to infinity, and then this is common to both. So, you get here this minus 1 times 0 to infinity . That is the final expression. Now, you can actually just multiply this inside. So, you find here, so there is a minus, okay, is outside 1 over 2 pi I, and this removes the one factor of 2, it makes it 1. So, this gives you e to the I pi z minus 1 minus e to the minus I pi z minus 1 times this integral. Okay. Now, this is what 2I times 2i times sine pi z minus 1. Sorry, it's a bit of a mess here actually. Yeah. So this expression therefore, so what the final conclusion is 1 over this, we are just started from 1 over gamma 1 minus z. We have shown that this is equal to, okay, 2i cancels, so there is just a minus pi, minus 1 over pi. I'm not sure if I made a mistake in this minus sign, but okay, that times sine pi times z minus 1, right? Sine pi z minus 1 times times this integral, okay, times 0 to infinity e to the minus t to the z minus 1 dt. Okay. And now this is where we now use the other identity. The identity was, which we all just proved, that gamma z times gamma 1 minus z was equal to pi divided by sine pi z, okay, which is the same as this equation. Okay. So just take this expression and multiply by pi divided by sine pi z, right? That will give you an expression for gamma z. This is just, so logic was that this was the expression that was the first integral representation for gamma 1 minus z. Then we went through this manipulation, right? In particular, focus on the real z positive situation. Then we found that this part of the integral vanished, right? That vanished only for real z positive, otherwise it wouldn't vanish. And then the result of these two integrals just gives you, as this is to be expected, right? Because after all, there is a branch cut here, right? So the value of this integral in the upper and the lower one will be related by a phase actually, and that is this phase. So that's why it's always a difference, this phase minus 1. This is what you get in such kinds of integrals, and that combines together to give you sine pi z minus 1 divided by pi. Okay. So now just take this equation and multiply by pi divided by sine pi z. Okay. So let's write it here. So what we are saying is that gamma of z is equal to pi divided by sine pi z, 1 over gamma 1 minus z, and now use that expression for this. You get here, okay, so I'm multiplying by pi times pi cancels, so there is still a minus sign here, sine pi z minus 1 divided by sine pi z times the integral 0 to infinity t to the z minus 1 dt. But this is 1, right? I mean, yeah, this is 1. So this cancels, this whole thing is equal to 1, and that proves that I mean, you started from the first integral representation and you arrived at the second integral representation. So the two things are equivalent. Okay. Any questions? If real z was not positive, you couldn't have gotten that, because this part of the integral would not have been 0. See? So there will be additional pieces. Okay, I think this is basically all. Yeah. Yeah.
Why we are interested only for positive volumes of Z?
No, not that. I mean, what I wanted to show is that this expression and that expression are the same in the appropriate range. So, but this is defined only for positive part, because otherwise it's divergent. This integral doesn't make sense. So, at least, so what we want to show is that this expression gives you this expression for this in this range. Right? I mean, this is defined everywhere, but that is only defined in the positive. Okay. Finally, the last thing since we already did that thing, you remember the expression that we had started with when we did the Stirling formula. I mean, that saddle point approximation. What was the example here? Yeah, and this example was. I think I can erase now. No, this part I can erase. Okay. Yeah, the example we studied when we discussed the saddle point. Approximation. The example we studied was this one, I, W, which was, sorry, what is? E raised to the W? W of Z, huh? No, sorry, I mean wasn't it, sorry, I cannot, okay, Z to the W times e to the minus Z, right? Was it e to the minus Z? Okay, I cannot. This is an equation number 31.38. Yeah, it is minus Z. Huh? That was integral. And integral is from 0 to infinity. Okay, instead of Z, let me call it T. Huh? Let's call this T. Okay, and the integral is from 0 to infinity. Okay, IW. And we showed that this was the leading behavior in the large W when W goes to infinity limit. This was IW behaved like root 2 pi times e to the minus W times W to the power of W plus half. Yeah, this is what we showed. Huh? But now if you look at this expression, I mean the integral representation we had for the gamma Z, which was that's our expression, 0 to infinity e to the minus t, t to the z minus 1 dt, then you see that this is exactly that integral. Just replace W by z minus 1, right? So what we are seeing is that, so we are saying that, so actually if I just look at gamma of z plus 1, then that expression is exactly the same, right? This is just take gamma z, z replace z by z plus 1, so you get that. So we are saying gamma of z plus 1 is going like, or better just to do this gamma of z, better just keep it as it is. All I have to do is just replace W by z minus 1. So we are saying the gamma of z in the large z limit goes like root 2 pi e to the power of minus z minus 1, right? W is replaced by z minus 1, and then z minus 1 to the power of z minus half. Okay, this is the behavior. So it's I mean it's a very this you see it grows very rapidly, huh? Because I already told you that this one you can rewrite this as e to the power of W log W minus 1, right? I mean, this you can write as e to the power of w plus half times log w, right? And then you can take the factor which comes common with w is this, and then okay, there is an extra piece plus 1/2 log w. But this one, you see, for w large, log w minus 1 is already going to infinity. You can ignore this 1, log w goes to infinity. And then on top of it, I'm still again multiplying by infinity. So it's a very rapid exponential growth. It is faster than e to the w, because it's multiplying e to the w times some infinity, right? So it's very rapid growth. So and again, combining with the fact that gamma of z is factorial, I mean, for z positive integer, it's factorial n minus 1. Okay. Or so in fact, what this is saying is that if I take gamma of z plus 1, this goes like exactly that expression, root 2 pi times e to the power of minus z, z to the power of z plus half. Okay, gamma of z plus 1. But this for z equal to integer, this is simply factorial n if z is equal to n, right? So we are saying factorial n grows like root 2 pi times e to the minus n times n to the power of n plus half. This is the growth rate of the factorial n. And factorial n, you know, it has to do with the probabilities and so on. For example, if you ask the question, if I have n objects and n boxes, how many different ways I can put these n objects in these n boxes? And that is given by factorial n. So this gives you how the probability, I mean, number of ways, how many grows rapidly with n, which is quite useful. It appears a lot in the statistical mechanics and probability theories and so on. These estimates appear. We will also use, when we discuss the hypergeometric function, again we will use the Stirling formula, okay, to obtain certain informations about the hypergeometric functions. So this will be quite useful. It's a very important formula to remember, in fact.